In this series of videos I'm designing a Z80 based computer system. So far I've built the video output system. I'm using discrete logic throughout as much as I can and trying to design this as you would back in the early 1980s. So I've got the video system working, I've got the core Z80 CPU system working, and what I was showing in the previous video in this series was the video output hooked up to a small microcontroller card. I was just using this to send some data through to the video card just to make sure that it works. Now all this circuitry I will eventually put onto a single larger PCB, not including the microcontroller of course. And I was outputting data in the previous video, seemed to be working, but I was outputting the data fairly slowly. So what I've done now is removed all the delays that were in the PIC microcontroller code, and it now sends a character every 10 microseconds. So we'll power this up, see the rate at which we can output video data to the display, and then we'll move on to the next stage in the project. So I'll get this powered up. Take a few seconds for the monitor to appear. I'm just going to dim the lights a bit. So as ever, ignore any flickering you can see on the display or any banding. That's just the camera shutter. But as you can see, we can now write an entire screen of characters in just a few milliseconds. So it's working extremely well. We've got very good speed out of the system. It's easily more than adequate for what we need. I'm not getting any weird artifacts on the screen, so it's looking like the video output is doing exactly what we need. All the addressing is correct, so if I write to a particular address, bear in mind that the video system doesn't really understand characters and rows and columns in terms of its SRAM address. It's just something that the Z80 will need to keep track of. But in terms of what I'm expecting to see for a particular address, then that's working fine. So address 0, for example, is the top left hand corner, and address 1920 is the bottom right hand corner, which is exactly what it should be. But as you can see, it's working reliably, and so the next step is to get it hooked up to the actual Z80 and see if it can still do the same thing. Won't do exactly the same thing. This will just output a single character, and we'll expand on this later, but for now I just want to make sure that the Z80 system can play well with the video output card. So I'll get this hooked up and we'll see what happens. So as you can see, I've removed the microcontroller card and I've got the Z80 board connected. So what I've got connected at the moment are the address lines, and I've got those going into the buffered address line outputs of the Z80. So for anything we add from now on, we really need to use the buffered outputs. We can't keep loading up the data bus and the address bus of the Z80. At some point it will start to complain. And this will give us better performance as well. It will guarantee that we get better signals going through to our ancillary circuits. So I've got the address lines, got the monitor connected in the same way it was before. We can now bypass the resistors. I had the resistors on this board because we weren't connecting to the actual Z80. We were using a microcontroller card, and they're not particularly well behaved when they power up, so we didn't want to do any damage to the video card. And we've also got the data lines connected, and we have the read, or the enable I should say, line from the Z80. So this is the line that selects the SRAM on the video system, and then we now use the dot clock. So I've been able to get rid of the signal generator, and we can run the video board directly from the clock of the Z80. One other thing I've now got connected up, I mentioned that to remove the artifacts from the screen when we're updating the SRAM on the video board, I'd already designed a hardware solution for this, but it wouldn't work with the microcontroller card simply because this was updating the video card asynchronously. It's got its own clock, and so there was no kind of synchronization between what it was doing and what the video card was doing. But now that we're running the video from the Z80 CPU clock, they're all synchronized, so that circuit will now work and it's hooked up and it removes the artifacts we were seeing on the screen. So it's hardware function, we don't need to worry about that in software, and that's kind of the design philosophy I'm using throughout, is if we can put something in hardware and remove the need to handle it in software, then that will help us later on. I've fitted the 2 buffer chips, of course, for the address lines. We need those because we're now using the buffered address. I've still got the control lines we're not using attached to 5 volts. That's just to stop the things like the interrupt kicking off when we're not using it. We'll come back to that shortly. And I've written some test code. The test code doesn't really do very much. In theory, it should clear the screen, so it just fills the SRAM, or at least the part of it we're using for the display, with spaces. That should clear the screen, and it then puts our 2 words onto the screen, or at least it should do. So this is quite an important test. With the PIC, we were just writing and controlling the lines going to the video card in software. But of course we don't really want to do that with the Z80. We want to be able to just write to the SRAM using a memory write in the normal way, normal memory write cycle. So if we want to update a cell within the video SRAM, we want to do that using a standard memory write instruction cycle. We don't want to have to start toggling control lines in software. So the timing and the way that the video board works is quite important now. If we got this wrong, then we'll get all sorts of weird behavior when we try running this. If we've got the timing right and it responds properly to the read, write and memory decoding signals, then we should get something appearing on the screen. And of course this does also test the memory decoding and the bank selection, because if they don't work, again we won't be able to select the SRAM. Our testing up until this point has been to read and write to the DRAM on the Z80 board itself. So we'll get this powered up, we'll see what it does. I'll just move the camera back initially so you can see these cards and the monitor, and then I'll zoom you in later to the monitor so you can see what's going on. Okay, so I'll get this powered up. So it's clearer what's going on. What I'm going to do is hold the reset key on the Z80 board until the monitor has had a chance to warm up. Otherwise, by the time the monitor's showing anything on the screen, this will have completed its task and it may not be clear what's actually going on. I'm also going to dim the lights a bit so you can see a bit more clearly what's going on the monitor. So I'll press the reset key, I'm holding that down. I'm now going to power up the Z80 board and the monitor, and in theory we should get the normal garbage showing on the screen. The video system continues to run with the reset key pressed, and hopefully you can see on the screen we're getting our usual garbage. If I now release the reset key, the screen should be cleared by the Z80, and then we should get a couple of words appearing close to the center of the screen. So we'll try that and see what happens. And it is indeed working, so that's very good. There's no weird artifacts that I can see on the screen. It looks to be fairly clear text. We'll try resetting. This should just repeat the process. It will clear the screen and then rewrite the 2 words, which it does. You may be able to just briefly see it flicker where it clears the screen and rewrites the text. So that's looking quite promising. The other thing we've got hooked up is the cursor control, and in the Z80 test program I'm actually putting the cursor out onto the last letter of the second word. So if I now connect that line up, I've got it disconnected at the moment just to allowing us to see what was going on. But if I now connect that up, it's bit 7 of the data bus. If we now reset the Z80 so it rewrites the data, we should see the cursor appear on the last letter of the second word. So we'll do that now, and indeed we have got the cursor appearing. So I'll just move the camera a bit closer to the monitor so you can see it more clearly. Hopefully you can see that. I'm just going to put the jumper back so that we're disabling the cursor generation again, and then we'll reset the board and the cursor should disappear, which it has done. So that's working fine. Just move the camera back again. So that's quite a big step forward. We now have what really amounts to a fully functional computer system. Now, of course, there are functions missing which we now need to start to add, but because we have the basis for a running computer here, we've got the core CPU running, we've got the memory decoding, we've got the main memory, we've got the video memory, and we've got all the refresh in place, we've got the ROM. So we've got everything we need here now to start building up towards our final machine. Quite a few things to add yet, so we've got a lot of work to do, but this is a very good first step. But the next thing we need is some way to interact with this, because a lot of the work we'll have to do will be to develop a boot ROM for this to allow the machine to start up, to load an operating system if that's what we want to do, have a monitor program so we can maybe enter programs through a keyboard. But I don't want to go down the usual easy route with this. The way of doing things at the moment for simple Z80 systems seems to be to hook up an RS-232 port and use a terminal, which is fine if that's what you want to do. There's no problem with that at all. But the stated goal for this project is to build what amounts to a full Z80 system. Now, having said that, the next step is going to be a kind of a bit of a contradiction on that. The thing we need to add next is the keyboard, so we can send data to the computer, so we can interact with it. At the moment we can't really do anything other than run code within the ROM, and that seems to work fine, but we really need now to add a keyboard so we can start developing our actual code that we'll need to run on this. So the next question is how to go about adding a keyboard, and I've given a lot of thought to this because it's one of those areas that could get very involved and it could get quite expensive, but I want to make this system accessible to anyone that wants to kind of follow along, and especially if you buy the book, I wanted anyone to be able to effectively replicate what I'm doing here without having to spend a huge amount of money, and making a custom keyboard would be very expensive. So I decided against that. Instead, what I'm going to do is use a PS2 keyboard, and that might seem, as I said, like a bit of a contradiction in what we're trying to achieve here, but PS2 is a vintage keyboard design anyway. It came out in the 1980s, so it is fairly old. It's also, you could use a PS2 keyboard as the basis for a matrix scanning type system. There's normally a membrane in there that you can hook up to. But I've decided to use the actual normal output from the PS2, but we need a circuit to be able to connect to that. I don't want to use a keyboard controller or anything like that, and also I don't really want to start using a bit bashing technique to connect to the PS2 keyboard. That's kind of what you'd do if you were using a microcontroller, but we're trying to design a discrete logic machine here, so I want to design a discrete logic interface for the PS2 keyboard. It's not very difficult to do, but that's what we'll do in this video, and then in the next video we'll look into creating an interrupt handling system for our computer, because with the keyboard ideally we need to use an interrupt system for getting keystrokes from it. If you don't do that, the timing for it becomes a bit tricky, and you end up with a machine that's unpleasant to use, because you'll get varying length delays between pressing keys and something actually happening. So it's best to use an interrupt system for handling keyboards. Also, we're going to need an interrupt system for a lot of the other circuits we're going to add to this. So in the next video, as I said, we'll add the interrupt, but in this video we'll look at the keyboard interface. So I'll get this out of the way and I'll show you what I've designed so far. So I've got a PS2 keyboard hooked up to the circuit I intend to use for this design. And before I explain how the circuit works, we'll have a quick look at the data that comes from the PS2 keyboard. If you're not familiar with the PS2 interface, it's been around for quite a while, but it is a very simple interface, and there are a couple of shortcuts you can use to interface with it if you want. So the first thing is that when you press a key on the PS2 keyboard, it sends out a short data packet. So in this case we'll capture that. So I'll press a key, and notice we've got the yellow line is the clock lines. There are two data lines that come from the PS2 keyboard. 4 lines in total. We've got 0 volts, plus 5 volts, the clock and the data line. So the yellow trace on the scope is the clock, and that's generated by the keyboard itself, and the purple trace is the data that's coming from the keyboard. So if we do a few captures, single shot captures, I'll press different keys and you'll see the data changes in response to whichever key you press. So it sends a scan code that's encoded, very like RS-232, except this is 11 bits long, and the first bit is always a 0, so the first data bit's always a 0, and the next 8 bits are the data. That's followed by a parity bit. It uses odd parity, and then we have a stop bit, which is always high. The data changes when the clock is high, and then we read it when the clock is low. So it's a very easy interface to deal with in terms of decoding the packet. Where it gets a bit more complex is if I zoom us quite a long way out and we do another single shot. And what you'll notice is there's more than one data packet being received. So what the PS2 sends is the first data packet is the scan code when we press the key, and then when we release the key it sends a special code followed by the same data packet again. So it will send the scan code for the key. It then sends a data packet that contains a data value of F0, and then it sends the same scan code again. So it does that when you release the key. So not only do we get data coming when the key is pressed, but we also get data when the key is released, and the sequence allows us to determine which of those events it was. So if we get an F0, we know that this is a key release, and the next data packet will be the scan code of the key that's just been released. So the shortcut I mentioned, or the first one, is that because of the number of data bits, what you can do is just count up to 23 data bits starting from the first bit, and then you can capture the next 8 bits, and that means you don't have to worry about which particular part of this packet it is. You'll always get the scan code for the key. The downside of that technique is you can't distinguish between keys being pressed and released, and also when the keyboard repeats, if you hold a key down it will start repeating. You'll need to be able to handle that in your system. So it's not a good way of doing it, but it's a very cheap and cheerful way of capturing data from a PS2 interface. But we don't want to do that. We want to be able to capture all the data packets so we can properly process them. The other thing to bear in mind with the PS2 is that although you have what you might perceive to be uppercase and lowercase characters, the keys for a PS2 keyboard only send one scan code. So for example, the A key only has one scan code associated with it, so it does not send a separate scan code for lowercase a as opposed to an uppercase A, for example. it's the same scan code irrespective of what key combination we press. So if we do another single capture and I'll press the A key, what we'll notice is if I then try to hold the Shift key and press the A key, it doesn't do what you might expect it to do if you're not familiar with these. So I'll press the Shift key first and notice it's sent a scan code. If I now do another single capture, notice it's continually sending scan codes until I release the Shift key. So in other words, it's continually sending a scan code that's related to the Shift key, and that's what your system has to cater for. The scan code you get from the A key is always going to be the same, and that is irrespective of whether you have the Shift key held down. So your system has to be able to determine if you're in shift mode, and then you will interpret the keys accordingly. So that's something that you have to do in software yourself. And if you look at the scan code table, you'll also notice that the scan codes themselves, so if we look for example at 0, if you're familiar with the ASCII scan codes, you'll recognize that this is not the ASCII scan code for the 0 key, and that's typical for pretty much all the scan codes. The PS2 interface does not output ASCII character codes. They are consistent across all different PS2 keyboards, but again your system will need to interpret the scan codes and convert those into ASCII codes if that's what you intend to do with them. So what we have to do with our system is be able to identify the incoming data, interpret it accordingly, capture the 8 data bits. We have to ignore the other data bits. You might want to look at the parity bit if it's important for you to be error free. You can either do that in software or hardware. I've decided to just ignore the parity bits. It's not that critical for us in our system. It's something we can add later if we want to, but initially we'll just ignore it. And so we're just going to capture the 8 data bits. So now we'll have a look at the circuit and see how it works. So as you can see, this is a very simple circuit. The LEDs are only here so I can demonstrate this, but what we want from this to hook it up to our system is to be able to generate an interrupt whenever a key is pressed and then capture the data. One part of this is not actually on here, which is the data buffer. So what this comprises is a shift register. It's an 8-bit shift register, and all we do really is shift the incoming data through the shift register. Now there are 9 bits that we'll have to shift up to the end of the actual data part of the packet, but that doesn't matter. We can just shift that through, and if we shift 9 bits through, the first bit we start shifting will be kind of shifted out. It will effectively overflow, and what we'll end up with when we stop will be the 8 data bits that we're interested in. And we need to be able to generate an interrupt when that occurs, and also we need to be able to stop the shifting at that point, because we don't want to carry on shifting the bits through, otherwise they'll be offset and out of place. So what we have is a counter. That counter is reset by this line, which I'll come back to in a few minutes, but it starts counting as soon as the first clock pulse is received from the keyboard, and it's arranged so the polarities work out correctly to capture the data. That same clock from the PS2 keyboard also clocks the data into the shift register, and then the IC at the bottom here is just a simple gate to allow us to determine when to stop counting, and it also allows us to gate the incoming clock and stop it being fed through to both the counter and the shift register. So that all works together. It counts the correct number of bits, shifts them into the shift register, and then it stops the process and it prevents any more bits from being shifted in. And the output from the shift register is shown on the LEDs. Normally these outputs would go through to a data buffer. We can't connect the output of the shift register directly to the Z80 data bus because it doesn't have tri-state outputs, and of course that will cause us problems on the Z80 system. So we'll have a tri-state buffer, and the enable pin from the tri-state buffer will be controlled by this line. This will come from the read enable line of the Z80, and it will do two things. Firstly, it will enable the tri-state buffer so it can output the data that's been captured onto the data bus, so the Z80 can just read it as a standard memory device or an in-out port. But also this resets the counter, so the red LED is connected to the halt output of this circuit, if you like, and so when this LED is on, it's indicating that the circuit is halted, and that same output is what will be used to trigger the interrupt on the Z80. So this red LED is on whenever the data ready output is low from this circuit. So the yellow jumper does two things. It will normally, as I say, come from the read line from the Z80, and as soon as that goes low, which it will do when I unplug it, so pull down resistor, it will reset the circuit. It would normally, as I say, enable the data buffer so the Z80 can read in the data. You notice it doesn't clear the data, so it doesn't reset that, it's still there, and so the Z80 would now read the data. It then finished reading, it re-enables this, and then when we press a key on the keyboard, it captures the next data packet, and then the Z80 can read it, and so forth. So it's a very simple circuit, but it kills two birds with one stone. It allows us to put the data from the PS2 keyboard onto the data bus, but also it kind of automates the reset and re-enable function within the circuit so that we don't need to then explicitly re-enable this. Also, it means that as soon as the Z80 has read the data is, or this circuit is re-enabled while the Z80 is processing the keystroke that's just been read. So this circuit can start capturing the next serial data from the keyboard while the Z80 is busy processing the previous keystroke. So all we'll need to do in our software system is create an interrupt handler that will handle the incoming keystroke, read the actual keystroke. That action will cause the circuit to reset and re-enable, and then we'll just need to interpret the keystroke data and turn that into an ASCII code and probably put it into a buffer so that we can handle more than one keystroke. So for example, if it's a shift character, we might want to store both the shift key. So if I re-enable this, which it is, and press the shift key, then you'll see that we get a character coming through. Also notice that the left shift and right shifts are actually different. So the left shift has this pattern and the right shift, as you can see, is different. But it means our system in software can then properly interpret all the key presses. We've got a very simple circuit. It's just actually just be 3 additional ICs because the gate at the bottom, we already have a few of those spare on the Z80 board. So very simple interface. All we'll need to do to make this work within our Z80 system is add an interrupt controller, which we'll do in hardware, and we'll do that in the next video. It's quite an interesting project in itself. Again, very simple to do, but we'll be going for mode 2 interrupts on the Z80 to make the system as flexible as possible, but we'll need to be able to put the interrupt vector onto the data bus in response to any devices like this generating an interrupt. Again, very easy to do, but be quite an interesting mini project, and we'll get onto that in the next video. One final point to make with this circuit is a PS2 keyboard will actually accept quite a few commands, so the interface is bidirectional. all I've shown here is data coming from the keyboard into our circuit. If we want to send commands out, then both the clock and the data line are open collector as far as the keyboard's concerned. There's a pull-up resistor at the keyboard end. So if we want to be able to control the keyboard, it's quite simple, and there's a relatively simple protocol that you go through. You pull the clock line low, wait until the keyboard's had a chance to recognize that, you release the clock, and then you can start sending data in response to the keyboard sending out clock signals. And the sorts of commands, there's lots of different commands, but the basic commands that we might want to add are to turn on the LEDs for num lock, caps lock and scroll lock. There are LEDs on here, but although there's what's labelled a caps lock key, it's not actually a caps lock key. Again, that just sends a scan code in the same way that any other key does, and then it's up to your system to return a command to the keyboard to turn on the appropriate LED. We'll probably add that at some point. It's very easy to do. We'll just use open collector buffers on our system and just send the appropriate string of commands. We can do that very simply from software. But it won't really require any modification to this circuit. All we'll do is we'll hook the outputs from our open collector drivers directly to the clock and the data lines. But I'll come back to that in a future video. For now, I'm only really interested in getting data from the keyboard into our system.